Okay, in this video, I'm going to demonstrate through a simulation a phenomenon called the Doppler effect. Doppler effect is a very important aspect of nature. We see it happen with light sources, sound sources, even ripples in water. So the purpose of this video is to give you a visualization of what the Doppler effect is before we discuss the definition and some concepts that go with it, and then eventually equations. I'm also going to show you some videos as examples of the things I would try to show you in class if we were meeting. Okay, so what is a Doppler effect? Well, before we can do it, let's start with a baseline. I'm going to look at a source of waves represented by this red dot. Okay, and I'm going to start creating waves, at least simulate. So here is a representation of those waves. Okay. And what do we see about those waves? So first of all, they don't look like the crest and troughs we showed on the notes because we're looking from above. So these are like ripples in a pond where each crest is the white circle or part of the white circle. There's troughs between them, halfway between, but we're not worried about that. So two things I want us to notice right away about this wave field is we have the brightness of the white gets less and less the further away. So that's a way of indicating the intensity, the energy, or the amplitude. Okay, that's not the main issue here in terms of the Doppler effect, but I just want to point that out if you're wondering. The other thing I want you to notice is the spacing of the waves. In other words, the wavelength. So they're equally spaced in all directions as you'd expect. The wavelength is uniform even if the amplitude gets less and less. Okay, so we also have a microphone where we can listen in on this if this was sound. So I'm going to just place the microphone right there, press play. Okay, so you hear the relative loudness. If I move it further away, it's not as loud as we expect. And if I move it closer, it's loud. Okay, but that's not the Doppler effect. Now, what I want us to understand is what we're hearing, the clicks, 2 clicks per second, is the frequency. Okay, so we can see that the frequency is 2 clicks whether I'm here, here, here. It doesn't matter where I am. So the frequency is uniform in all directions. All right, so if we were to represent this on a graph, the frequency is a function of where we are, right? We would just draw a flat line. So let me go to draw, maybe. And so there's a flat line. I'll call that F naught. That's our reference. Okay. Now, let's bring in the idea of the Doppler effect. So what is the Doppler effect? Doppler effect occurs when we have either one of two things happening. We either have our source of waves move or the observer moves. So I'm going to demonstrate where the source of waves moves first because that's the easier thing to visualize. So what I'm going to do is I'm going to go to a speed setting here to where it says 0.5. There's nothing special about the 0.5. It's just a convenient number. So what this speed is, it's not moving, the source itself is not going to move 0.5 meters per second. It's going to move half the speed of the wave. So the waves are propagating out at a certain speed based on the medium itself, not the object. And this is a really important point. Whether this object is moving or not, the speed of the waves is the same regardless. So if you're in a car moving down the road, the speed of sound of the engine is the same regardless of whether it's sitting still or moving really, really fast. Okay, so Doppler effect is not so much about the speed of the waves. So let's move our source, and it's going to move to the right. And now you are seeing the Doppler effect. Okay, so let me pause it for a second. What are you seeing? Well, you see in front, if I'm standing here where the microphone is, I observe the waves are much closer together. In other words, there's an apparent wavelength shift. And if I were standing back here, I would see that the waves are further apart than they were originally. So I have a longer wavelength here, a shorter wavelength here. And if I were standing on an axis that's perpendicular to the motion, actually the wavelengths would be the same as the original. It might be hard to see. Now, it's easier to understand what's happening by using audio. So let me start it again. And let's listen in terms of frequency. Okay, so we hear nothing until the waves hit us. And notice, as it's coming at us, those clicks are much faster. In fact, you look down here, detected frequency is about twice what we originally had. You're hearing 4 clicks per second. Then it passes through us. And if you look at, or listen, I should say, you hear it's about half the frequency, or not quite half. So the frequency detected behind it as it's moving away is less. when it's coming towards us is the same. If I move it to the side, all right, and it's going to be hard to hear, or it's going to be very short-lived, it's essentially the same as before. Now, as it moves away from us, it gets less and less. So in terms of the graph, what we have is when it was coming towards us, in other words, actually, this is probably going to mess this up. Yeah, didn't want that. Ignore that red line. So when the microphone is here, in other words, when the source is moving toward us, we heard a higher frequency, higher than the original. So if we draw a transition, forget about that line, we would hear a consistently higher frequency. Okay, and notice that I've drawn it so it's flat. It doesn't depend on where you are, how far away. The intensity does, but it is higher. So I'll call that F prime. So F prime, when it's moving towards us, is higher than when it was stationary. And then when it moved away from us, so this is towards us, higher clicks, normal, and then lower, we get a drop in the frequency compared to the original. So if I were to go back to where this was, as it passed through us, we would have a transition. Again, don't worry about the slope of that transition, where we would have a new one where I'll call that F double prime. Okay, so if the source is not moving relative to us, it's normal frequency. If it's moving toward us, a higher pitch. If it's moving away from us, a lower pitch. And I use that word relative, and that's super important, because if you're the source of waves, let's say you're in a car that's honking a horn or sirens, you would hear just a normal F. In other words, you're not moving relative to the source because you are part of the source. But if you're an observer outside of that, depending on which way it's moving, towards you or away from you, you hear very different. And you can see it differently in terms of wavelength. So I'm not going to write down those notes or details because we'll get them later. And if I want to, you're wondering what determines how scrunched together they are, it's pretty straightforward. It's basically how fast you're moving. So if I make the speed pronounced compared to the speed of the wave, okay, you can see that they're really scrunched up, right? There is some tiny wavelength there, okay, and behind it's really stretched out. So you got a really high change in frequency and then a really low change in frequency. And if I were to go faster than the wave, then I get something else that we'll discuss later on. That's called a shock wave. If you've ever been around an air show where speeds go, or planes go faster than the speed of sound, that's a shock wave because you're outracing the waves that you are producing. But we won't worry about that. Okay, so that's the Doppler effect in a nutshell. You have a source of waves that's moving relative to you. If it's moving towards you, you hear a higher pitch or a higher frequency, because pitch is for sound. If it's moving away from you, you hear a lower frequency or you observe a lower frequency. Now there's another way you can get the Doppler effect. Okay, I'm going to turn this to 0. I'm not going to have my source of wave moving. And you see everything's fine. But listen to what if I move the microphone? In other words, let's say this is a stationary siren and I'm moving towards it. So the waves aren't reaching us. So I don't know if you caught that. So if I'm moving towards it, let me try that again. Move it quickly. I'm not doing a good job. But I guess I'm trying to get you to understand as I move it relative to source, I can hear a Doppler effect as well. Okay, the response time is not good enough. So it can be a moving observer. It could be a moving source, or they both could be moving. What matters is that we have relative motion. Okay, so when we do the calculations, we'll see there's slightly different equations for a moving source versus a moving observer versus both moving. Okay, so let me just show you some examples of that to finish up. All right, here's the classic example with sound. So notice as that car is coming towards us, don't worry about the loudness, is that the pitch is higher than normal. And then as it recedes away from us, you hear that shift where it goes to a lower frequency. Okay? So that's a very common example of a Doppler effect. High frequency and the low frequency. Again, ignore the intensity. Now this is fairly trivial. It's not a big deal, but it's an easy way to demonstrate it. More important, and this is another one, and this is just a simulation, is with light. So let's say this represents a star, a distant star, and it happens, and let's say the Earth is here, or one observer is here off to the right and another observer is off to the left. What would we see about that light if this star is moving? Okay, so and this is initially what it looks like if it's not moving. All the wavefronts are fine. Now it's starting to move to the right. And like before, the waves in front are scrunched up, the waves behind are further apart, but what I want you to notice is the subtle change you see here is the color. So initially, this star is a white star. It's putting out a bunch of different frequencies of light, so it appears white to us. But if you're in the direction of that it's moving, it will shift to a higher frequency of what you see, and that would make it appear bluer. Not blue itself, but bluer than normal. And if you're behind here, the waves receding as they're coming from you, they would shift to a longer wavelength, lower frequency, or it would appear redder. Okay, and that's called a redshift. And you may have heard that before in relationship to astronomy. So if there are objects out there that are moving away from us or towards us, then their light that we actually observe will be shifted to a different frequency, and that difference in frequency depends on how fast it's moving, and that's an extremely important measurement in astronomy. All right, Edwin Hubble, he basically used that to determine that the universe is expanding, but that's another discussion. Okay, so those are two examples of the Doppler effect. There are many others, and I'll summarize the key points in a tutorial.